So we've seen how we can build trees to help us classify and identify organisms based on their observable characteristics of those species and their phenotypes. But choosing the characteristics to use for building those trees is very important, because it can lead to some anomalies that mean that those trees don't always represent faithfully the evolutionary history of the organisms in question. So the question now is, can we use sequence information as a richer and more reliable source of information that we can treat objectively to establish evolutionary relationships between organisms? So can genomes give us less ambiguous information for building phylogenetic trees? Well, the first thing to mention is that genome sequences really do give us a very large amount of information. The very smallest genome sequence, 1 nucleotide long, can have 4 different values at each position. 4 different nucleotides are possible. There are 4 different 1 nucleotide sequences in the world: A, C, G, and T. That's not a very large number. However, 2 nucleotide sequences, there are 16 different sequences of 2 nucleotides long, and as soon as you go up to 3, it becomes too many to write down on the slide, because there are 64 different trinucleotide sequences, and so on as the sequences get longer. Now the formula is that there are 4 to the power n alternate sequences, where n is the length of your sequence. And that little formula gives you a curve that goes up very rapidly. Here is the number of different sequences on a logarithmic scale against the length of the sequence in nucleotides. And you can see that even by the time you've got to 20 nucleotides, the number of different sequences you can have has got to a very large number. In fact, it's about 10 to the 12. And by the time you get to a sequence that's the size of the smallest sort of gene you can have, 1,000 nucleotide gene and able to encode 300 or so amino acids, the number of different sequences that can have that length is truly astronomical, 10 to the 602. So there's a vast amount of variation in sequences available to us, which we should be able to use if we could analyze them objectively. Now let's just imagine that we really start off knowing the evolutionary history of a short sequence, and let's just play it through. Let's say our ancestral sequence is this one, and it's got in the middle of it, I put it in bold here, the Gattaca sequence that you'll have heard about as the ECAR1 restriction enzyme site. Let's just imagine that that ancestral sequence gives rise to progeny, amongst which there's one which has got a single point mutation, introduction of a T at that position in red, replacing an A. So a single nucleotide substitution. And that little sequence, a B sequence, gives rise itself to a daughter sequence where the second T is mutated to an A, which I've shown in purple, in sequence labeled D, but it also gives rise to another sequence labeled E, in which a different nucleotide is changed, a C for a T in blue there. And then finally sequence E gives rise to daughter sequences F, in which one of those A's is changed to a C in magenta, and another sequence in which the final A has changed to a C in magenta. So we've got a little family of sequences there. And we know, because we've followed their evolution, we know how they're related to each other, and we can see how that makes sense. But if you imagined that we only now, today, have in the world the final sequences D, F, and G, and that the ancestral sequence and the intermediate sequences B and E have disappeared. So if we've only got sequences D, F, and G, could we reconstruct just from their sequences that evolutionary history? Well, that would be a nice task. The first thing to note before we can start building the tree that relates the extant sequences together is that for any one set of 4 different sequences, there are 3 alternative tree topologies. That's the shape of branching of the trees. 3 and only 3. I'm going to label them A, B, and C in these slides. The topology A is one where the 2 sequences, numbers 1 and number 2, are closely related, but they're more distantly related from sequences 3 and 4. Topology B is one where the sequence 1 and 3 are most closely related. And topology C is the topology where sequences 1 and 4 are most closely related. And we need to find out for each node of a tree which of those topologies is correct. We're going to take an even shorter example sequence than the one I showed you before, and we've got 4 different examples of that homologous sequence that are shown on the slide now. We're going to try and work out what's the most likely evolutionary relationship between these 4 sequences given certain assumptions. And the rule we're going to use for this practice is called the rule of maximum parsimony. And in many ways it relates to the invention of a chap called William of Ockham, who lived in Oxford, Merton College, just a few yards away from where I'm talking to you now, in the 14th century. And he came up with what's been known as Ockham's razor, which is there in Latin. Shall I give it a go? Entia non sunt multiplicanda praeter necessitatem, which means don't make things more complicated than they need to be, or keep it simple, stupid. So let's apply the method of maximum parsimony to those 4 sequences. Remember, those 4 sequences can be arranged in 3 different topology trees, A, B, and C, and our job is to find out which is the most likely topology tree, which is the one which in this methodology it needs the fewest mutational changes to achieve. So we set out those 4 homologous sequences, and we've numbered now in purple there each of the 5 positions in those sequences. Homologous position number 1, number 2, and number 3, number 4, number 5, and so on. So we go through these 4 sequences that have been lined up site by site. So first of all, it's site number 1, where the first 2 sequences have an A, and the second, third, and fourth sequences have a G. So just at that first position, you could have any one of those 3 topology trees could be true. However, if the tree number A is true, you only need 1 change from the ancestral sequence to give you the arrangement of that topology tree A for position number 1. With either topology tree B or C, you would need 2 changes in nucleotide sequence. Whether the ancestral nucleotide was an A or a G, you would need 2 changes to get you to the observed topology tree. So because of that, topology tree A is a better, simpler explanation of the data than either B or C, so it's preferred. To build your maximum parsimony tree, you do that process for each site. And then you add the total number of substitutions that minimally are needed to generate your topology tree at each site for each of those 3 topology trees. And then you work out which of those 3 topology trees in total requires the fewest nucleotide substitutions. And you can see that for the trees A, B, and C, we've gone through site by site, measuring this minimum number of mutational changes needed to generate that tree. And you can see that of those 3 trees, tree A wins because it has the lowest number of mutational changes that you need to make it. So tree A wins, and that has that topology. So for these 4 sequences, the tree which best explains the data using the method of maximum parsimony is tree A. And so we can display these 4 sequences on a tree like that. And that's really helpful. However, you can see that at some of those positions, tree A wasn't the best tree. At one of those positions, actually, tree A wasn't the best tree. So what you also need to be able to decide is how certain you are that tree A is better than B or C. And so establishing the uncertainty level is something we do using a bootstrapping method. So here is our preferred topology tree that we have established for all 5 nucleotides 1, 2, 3, 4, 5. If we do a rather peculiar thing and sample that sequence, make a subsample of that sequence at random, and here we've repeated nucleotide position 2 but thrown away position 1, and we've repeated nucleotide position 4 but thrown away position number 5, and repeat the maximum parsimony approach to building the tree for this subsample, we ask the question, what would be the tree from this funny subsample? And as it happens, it's still the same tree, tree A. And we take another sample where we've kept in nucleotide sequence number 1, we've duplicated number 2 again, but we've thrown away 3 and 4 and duplicated 5. And for that, we also get the same. It turns out, when we do that many times for this particular sequence, we end up always getting the tree, tree A, the one we saw first of all. So we can say 100% of the time, this tree is the preferred tree, the one that satisfies the condition of maximum parsimony. So we put a little label 100 by the nodes to tell us that. And that's called the bootstrap value. So now you've got all you need to be able to read a phylogenetic tree from a research paper. So for example, here's one from 2008, Towner et al., talking about the sequence diversification amongst the filoviruses, Marburg virus and Ebola viruses. And on the right-hand side are each of the different isolates from different countries at different times, and the total genome has been sequenced, they've been aligned, and the method of maximum parsimony, or a similar method, there are 2 or 3 other methods that you can explore, which give you slightly different answers or different robustness under different conditions, have been used to generate the tree. And the 2 features of it that you're now familiar with is the number of substitutions, the minimum number of substitutions needed to get you from one part of the tree to the other, and that in this sort of tree is commonly shown as the length of the branches in that dimension. So that's giving you the scale of half a substitution per site is that length of branch. So those branches for those 2 Zaire isolates are very, very small, at 0 length, pretty much, so they're identical sequences. And the second figure you see on here is the bootstrap value. How confident are we that the topology of the tree is as we've shown it to be? Some of those branches are very, very confidently ascribed, some of them less so. So now you can go away and read papers with these sorts of trees on them, and you can understand how it's done. Clearly, for long sequences, anything longer than the ones we've shown here, you wouldn't want to do it by hand, even using the maximum parsimony method, which is one of the most straightforward ones, but you can see how computers can automate that process for you and enable you to generate these very, very rich trees from data sets with a great deal of confidence.